Dear students, I welcome you back for the course of railway engineering. Today, we will continue with the discussion on track stresses, and along with the rails, we will also try to discuss about the sleepers. In the previous lecture, we have emphasized only on the bending stresses and the moments which gets induced in the rails due to the vertical loads. But today, in the case of rails, we will be talking about the eccentricity. We will also be talking about the lateral load and the twisting which is being caused because of these eccentricity or the lateral loads, the lateral deflections, as well as the thermal effects. And then towards the end, we will be discussing about the stresses in the sleepers. Starting with the eccentricity. Now, stresses which are caused due to the eccentricity, if you understand that eccentricity here on the right hand side, a diagram has been given. There, if the loads are all along the axis, then the load could have been at this particular point. That is, this is the central vertical axis of the rail, but the load is at a distance e from the center, and that is where the eccentricity is coming, and that is where this particular load is going to make an impact in terms of not only the condition of the moment, but it will also try to take this down, and therefore, some of the twisting can happen in terms of going down of the rail section in this way. So, this is the problem which we are trying to talk here. Now, this eccentric load produces bending in the vertical plane and twisting of the rail, and this is equivalent to the torque at the middle as rail is held at ends. So, when we say rail is held at ends, so there can be a clip or there are other fastenings which can be provided so as to hold the rail here. So, in that sense, there is a possibility of those torques which are being created. This causes bending of the head and the foot of the rail, and this bending stress is nothing but this is half of the torque, or the torque is 2 times of m, where m is what, and this is also equal to TIV into E. TIV means this is the load which has been enhanced. We discussed in the previous lecture that what is this value of TIV and how we calculate the value of TIV because of the interaction of the two wheels which have been placed at a distance of 6x times. So, E is the eccentricity. So, this we are going to consider whatever this eccentricity is there, this depends on what is the position of the load, but then this is not a big area, it is a smaller area. So, accordingly you will find the eccentricities are within small some mm's or centimeter, small centimeters. The stress due to eccentricity here, the bending moment in the foot of the rail is given by a formula EI2 H2m into R divided by C. And similarly, in the case of head of the rail, it is E I1 H1 into m into R divided by C. So, E, m, R and C they are constant, but I and H, which is a moment of inertia and the height with respect to an axis for that particular side, is changing as H1 and H2. Now, R here it can be calculated by this formula, which is C divided by D into H square and under root of this whole value, and C is the torsional rigidity, which again can be calculated by a formula given here. And if we talk about this D, which is being used so as to compute R, then this D is E I1 I2 divided by I1 plus I2. So, it is a cumulative effect of the moment of inertia of the two sections along with the modulus of elasticity, and as E and I, this gives you a stiffness condition. So, we are getting some effective stiffness condition out of here, and H is this is the distance between the centroid of head and the foot of the rail. So, if we consider this is the centroid CG of the head and say if this is the CG of the rail, then this is the distance between these two centroids. And when we talk in terms of the axis, so if suppose this is the axis being shown here, and this axis gives you a condition that there is a possibility of a twisting, and if this twisting is happening here. So, if that twisting happens, then what will be the point which you get from the twisting axis versus this horizontal axis, that point will give you the value of H1 and H2 with respect to the CG of the head and the CG of the foot. So, this small h is nothing but this is H1 plus H2 overall. Now, this H1 is the distance of the centroid of the head from the center of the twist and can also be calculated using the characteristics here, which is nothing but I2 divided by I1 plus I2, and in the case of H2 it can be I1 divided by I1 plus I2. So, that is how those two values can be calculated. Now, the another value which is considered is a polar moment of inertia in the calculations, and then this G which we considered here, there is a G value and IP value, these two values. So, this is a modulus of rigidity of the rail, and A is the area of the cross section of the rail. So, bending stress due to eccentricity, this will be either positive or negative depending on whether we are talking about this Z as a compression side or a tension side. So, we can have plus M E I H into R divided by C Z or minus M E I H R divided by C Z. This is the information with respect to the various characteristics which we are considering here being given. Say for a 52 kg rail section, the cross sectional area is 66.15 centimeter square, the weight per meter is 51.89, height is 156 mm, the flange width is 136, the head width is 67 mm, thickness of the web is 15.5 and the height of the head is 51 mm. So, these are the different values for different sections already being given here. Now, let us look at one numerical. Say the TIV is already given to you, need not to calculate. We have calculated previously by using the speed factor and all those calculations were done for the previous numerical in the previous lecture. Eccentricity is given as 1.5 centimeters. So, this is 1.5 centimeters at which the load is acting. The combined value of EIHR divided by CZ for head as well as for foot, they are also being computed and given to you. So, it is 0.04353 per centimeter cube or 0.03105 per centimeter cube. We have to calculate the bending stress in the head and the foot of the rail due to eccentricity. So, when we talk about torque, torque was 2 times of the moment and it was TIV into V. So, from this what we can get is M is equals to TIV into V E divided by 2. TIV is given as 12.521, E is given as 1.5. So, considering those values what we get is 9.39075 centimeter turns as the bending moment. Now, because we have the value of M and the combined value of this is already given to us for the head and for the foot as you can see. So, we are considering those. So, here in the case of head, when we multiply these two values what we get is 4.09 kg per mm square. Similarly, in the case of foot if we calculate and we find out this value as 2.92 kg per mm square. So, these two values are being calculated and that is what was the numerical which was given to you so as to calculate the values. Now, here this is one of the graph which has already been given in the guidelines of the Indian Railways, and it is basically the stresses due to eccentricity of the vertical loads for broad gauge tracks. So, live load is being given here in tons and there is a rail stress in ton per centimeter square values being here, and then for head and foot conditions. So, this is head and these are the combination and then at the bottom there are the foot conditions. So, we can directly get the values here also. Now, another thing is the bending stress due to twisting or the lateral load. So, now we have a lateral load being applied here, say this is R which is being applied. Now, this R is being applied at a distance 5 mm below the top surface of the rail head. So, this is how it is being considered. Now, when you are talking about this lateral load, the lateral load is taken as 40% of the static wheel load and divided by 2. If you remember, this was discussed previously. The distance between center of twist and the point of application of the lateral force is defined as HF. So, this is the center of twist and this is the location where the load is being applied. So, if we are going from here to the top, it means there is H1 plus this height and this is the CG of the rail head. Therefore, we can consider that this is the height of rail head by 2. So, we will go to the top and then if we reduce 5 mm from there, we will come to the location of R and that will become HF. So, the same thing is being defined here. So, HF is the total H minus H2 plus depth of the rail head divided by 2 minus 5 mm. So, the torque is here the lateral force into HF. So, that is the value which will be there, and bending stress in the rail head or foot, it is again being taken by the same formula which we have discussed previously. So, let us look at one example here. We have a static wheel load of 18.8 tons. The value for EIHR by CZ for head and foot, they are already there. Depth of center of twist from the top of rail head, that is 10.409 is being given, but it says it is from the top of the rail head. That means now this HF is nothing, it is 5 mm below that top. So, you have to reduce that. So, HF will come as minus 0.5 here. We have to calculate the bending stress due to twisting or the lateral load R. So, the lateral load is here again 40% of what is coming on the one wheel side. So, if you have taken 18.8 divided by 2 into 0.4, so 3.76. So, the torque is 3.76 into 9.909. So, we got a value and this value is nothing but 2 times of m. So, what the bending moment which we are getting is the 18.62892 centimeter tons. Then bending stress, once you have got this value, you are now going to multiply it with respect to the value given for head and foot. For the rail head, the value was 0.04353. So, on the basis of that, what we are getting is 8.11 kg per mm square. And in the case of foot, it was 0.03105, and when we multiply it, what we get is 5.78 kg per mm square. So, this is how the bending stresses in the head and the rail foot can be calculated. Here again you can find that there are graphs being given for that. This is a static axle load in tons, this is the rail stress in tons per centimeter square. Then the conditions are given that there is a value which we are calculating for head, for a rail 75 R, for a sleeper density of m plus 4 and for a ballast cushion of 200 mm. So, if this is the condition there, then for whatever the given value of static load is, you can go upwards and then find horizontally you go towards the left hand side, you will get a rail stress. Now, there is a bending stress due to the lateral deflection of the rail under the lateral load. So, whatever lateral load is there, so because of that some deflection may get induced here. So, when this deflection gets induced, we are considering how the stresses will be induced, and that is what is to be calculated now. So, lateral bending moment is lateral load multiplied by the sleeper spacing, and the bending stress due to the lateral bending will be the bending moment which we have calculated divided by Z, as the same way as we have done previously. Z is nothing but the lateral modulus of section of the rail for either head or foot. So, let us come back to one example here. So, there is a lateral load which is 3.76 tons. So, our value is being given. Average spacing of sleepers is 83 centimeters. So, as soon as this average spacing of sleepers is there and the lateral load is there, so the lateral bending moment can be calculated. So, that is what is being calculated here. So, this is 3.76 into 83. So, so much of ton centimeters is the lateral bending moment. Then what other values are being given? The lateral modulus of section of rail for head and the lateral modulus of section of rail for foot. So, that is the value which is given to us, and that is where we are going to consider it as JAD. So, if this JAD is being considered, so bending moment divided by this JAD value will give you the stress. So, the stress due to the lateral bending in head of the rail is 78.02 divided by 96.323 as given at the top. So, this will give you a value of 8.13 kg per mm square, and in the case of foot again 78.02, which is the lateral bending moment being calculated, divided by 47.031, which is the value of the lateral modulus of section of the rail foot. So, what we get is 16.59 kg per mm square. So, this is the value which we may have. Here again you can see that the graphs have been given for that. Here on the x axis is the static axial load in tons. On the y axis again there is a rail stress in tons per centimeter square. Now, in this case again for foot and for the head, for the different rail sections, for different sleeper density and the thicknesses of the ballast cushions, the values have been given. So, once we have an idea that what type of track is being provided, means the thickness of the ballast cushion, the sleeper density, the type of the rail, then we will go to that particular line which is being shown here with respect to the static axial load in tons. Say if we are talking about a static axial load of in tons is 19 and it is a 90R rail with M plus 4 and 20 centimeter of the ballast. So, we will come up to this position here. So, this is the point, and then we will go horizontally outwards towards the left. So, what we get is somewhere around 1.73 as the rail stress in tons per centimeter square. Now, the combined effect of the different loadings, how we are considering that. So, the bending stress due to vertical load and eccentricity only in head or foot, it is longitudinal bending stress, but and stress due to eccentricity, we take a summation of these two. So, here we have talked about vertical load and eccentricity. Then another case is there is a vertical load, eccentricity and lateral load. So, the value which is going to be there for head, there is some change which is going to be there in the case of head and the foot. So, we have longitudinal bending stress plus bending stress due to twisting of rail plus bending stress due to lateral deflection minus bending stress due to eccentricity with respect to the directions, or you can say the compressive or the tensile condition which is being created by that particular type of load environment. This is what has to be taken. So, here bending stress, longitudinal, twisting and due to lateral deflection they are being added, and due to eccentricity is being subtracted. Similarly, in the case of foot, if all of these three things are there, then longitudinal bending stress due to eccentricity, due to lateral deflection and a bending stress due to twisting of rail has been now deleted here. So, previously it was due to eccentricity, now it is due to twisting of rail. Previously the twisting of rail was taken as positive for the case of head, now here it is being taken as negative. So, this is the difference between the foot and the head. Now, maximum permissible limit of the significant stress is kept as a fatigue limit of the rail steel, and this is taken as 45% of the UTS. So, if we are talking about the 77 UTS rail, then this is 34.7 kg per mm square. Now, another point which we need to consider is the thermal stresses. Some idea we are going to take here, and then further idea we will be taking in one of the other lecture. So, it is caused due to the variation in temperature. This is an obvious condition, and there is a de-stressing temperature. This de-stressing temperature is a temperature at which the rail is being made stress free condition, and there are different ways in which it can be done. So, this ranges between Tm and Tm plus 5 degree centigrade, where this Tm is the mean rail temperature, and this mean rail temperature is considered on the basis of a 5 years data. This variation, it may induce the maximum longitudinal stress of 10.75 kg per mm square in the extreme winter and a compressive stress of 9 kg per mm square in the extreme summer. And again, this is what we are repeating. We have already discussed about this in one of the previous lectures. Now, there are residual stresses which are caused in the rail due to the process of manufacturing, and there is a flexed laying of curves, or there is a sun radiation on one side of the rail, or there is a wheel flats or loose or hanging sleepers. So, these are also some of the issues, and they are all related with the maintenance of the track. Now, the permissible values which are there, the permissible stress in the rail due to vertical load, its eccentricity, the force which is being produced by the flange. So, that is a lateral force we are talking here. It can also be talked as a lateral value, and the thermal stresses. It is 10% less than the yield limit of the rail steel. So, whatever is the yield limit of the rail steel which is available to you, which is provided by the manufacturer. So, 10% less than that is going to be the permissible value in this with respect to the cumulative conditions. Now, yield limit of the rail steel is taken as 52% of the UTS, say for example 77.5 UTS rail, the yield limit is 40.3. So, permissible stress is 10% less, so it is 40.3 minus 4.03. So, what we get is 36.27 kg per mm square as the value. Now, in the case of short welded rails, this value is 30.25. In the case of long welded rails, it is 25.25 kg per mm square. So, this is already specified on the basis of the calculations. Now, margin has been made 25%. Initially, it was 10%, which we discussed. It has been changed, and with respect to those 25%, the new values can be 30.225, 24.25 and 19.25 kg per mm square. So, this is a new practice which is now being taken in Indian Railways. Now, let us come to the sleepers. Now, what are the factors which causes stresses in the sleepers? The very first thing is what are the type of loads which are going to be there at the top of the sleeper through rails. Now, rails have been placed at the top of sleeper, so there is a weight of the rail. If a locomotive is standing there, then the weight of the locomotive or the wagons will also going to be there. So, that means there is a wheel load, there is a transfer from one wheel to another wheel, that particular type of transfer of the weights can also be there, and that depends on the proximity of the wheels, and where we talked about the x and the 6x conditions. The effect of the speed, which do what? It basically augment the weight which is there, the static weight which is there. So, it will be increasing that by a certain factor. So, we have talked about the Talbot factor there. Then dynamic augment due to many other reasons can also be there, depending on what type of locomotive is being used. We talked about in the case of say steam, there were like a hammer condition or a steam condition, those things were also augmenting it. Then maintenance is always going to be a factor. If the maintenance is not good, then it will induce the stresses. We have discussed this previously also. We talk about the irregularities in the rails, we talk about the maintenance of the rails, and there is a maintenance of the wheels of wagons, coaches, locomotives. So, all of these together are also going to create some stress condition in the sleeper. Then there is a effectiveness of the supervision for ensuring the good maintenance. This is also an important thing. If it is not being done by the staff, is being left, then there will be certain sections in the track which will feel more distresses, and then the wearing and tearing or the various other types of defects which may appear, they will start coming at that particular location. And when we are talking about the components of the track in terms of the strength characteristics, the track modulus, which we have discussed as the initial track modulus and elastic track modulus. We talked about the elasticity of rails and its stiffness, the design and strength of the sleepers, because there are variety of sleepers based on the type of the material which has been used for the manufacturing of those sleepers. The things will change, the characteristics will change in terms of the strengths, the sleeper density. In the case of broad gauge, where we have talked about 1300 plus or 1500 plus or 1600 plus values, and the type and efficiency of the fastenings. What type of fastenings have been used? There have been old conventional fastenings versus elastic fastenings. So, nowadays we are working with more on the elastic fastenings. So, this also will make a difference, and how these have been embedded into the system, say if they are connecting the rail with the rail or they are connecting the rail with the sleeper, what is their quality, what are the loads which are required to be there, if they are there or not. So, all of these points will also make a impact. So, when we see here the distribution of the stresses, what happens is that this is a one sleeper, as you can see the load is getting transferred, say from this location to another location. As soon as the load comes at one particular location, there is going to be a deflection of the sleeper at this point, but there is no load which is moving here. So, this is a rail location. So, here also there is a rail and this one is also a rail. So, at a rail location only the load will be coming, but nothing is there here in between. So, because of this rail condition and the wheel is going to be there at this rail. So, it is connected by the axle here. So, the load is getting transferred to these two wheel conditions and coming to the rail and coming to the sleeper, that is where this deflection is going to be there on ends, but at the center nothing happens. So, if this type of a deflection scenario is getting created, this is defined as a center bound sleeper condition. But it says with the repeated application of loads, a depression is caused at the end of the sleepers. This results in the higher depression at the ends as compared to the center and called as center bound sleeper. Now, what is the maximum load on the rail seat? In this case, it is defined by P into S divided by Z into I, where P is the wheel load, S is the sleeper spacing, Z is the modulus of rail section and I is the characteristic length, and this characteristic length has to be calculated, and this is approximately 30 to 50% of the dynamic wheel loads. That means the static wheel load are already there, this has been augmented. So, that is the dynamic wheel load conditions. So, if we consider that, then can be taken 30 to 50% of that. And the length of the sleeper and the rail seat is so selected that under normal loading conditions, the middle part of the sleeper remains stress free or it remains with very less stresses. And the provision of the bearing plates also reduces the maximum stresses in the sleepers by about 32% on the broad gauge track. That means, here if at the rail seat if we have provided a plate first of all, then what will happen is that whatever rail is provided here in this form, so this load will come on the bearing plate and then gets distributed to a bigger area. So, this plate is will be something in this form, a rectangular or a square plate, and as this bigger area is there. So, this total area will be considered so as to come up with a pressure P and will reduce the effect in terms of a deflection. So, this is another point which can be taken into consideration when we are talking about the stresses in sleepers. So, with this we close our introduction now. What we have discussed is the track stresses, especially the bending stresses in the rail section due to eccentricity of the vertical load, due to the application of the lateral loads, due to the deflections caused in the lateral direction because of those lateral loads, the twisting of rails, as well as the thermal stresses. And then towards the end, we talked about the stresses which appear or occur in the sleepers. With this, we close this lecture. Thank you and bye.